You'll be like, how do they get this?
Well, except I already got all this up here. Well, it's all gone. Bye. Okay. It's recording, right? 12, 13. Okay. All right. Now, you're really good at this. I know you are. What is the antiderivative of the cosine? Sine, of course, obviously. Okay. And what's the antiderivative of the cosine of 2x? Okay, this is going to trip you up. Sine of 2x would be wrong. We got to fix it. Right. Whoa, you're good at this. And then, what's the antiderivative of a power rule? It's got to be. By the way, you know this rule, right? Do you know how to anti-differentiate a power? X to the 3 over 3 has got to get you back, right? Okay. So, wow, you guys are so good at this. So, all right, let me trip you up. It's really good. Negative 1 over 2x? That's, okay. Well, let's see. What would be the derivative of 1 over 2x? Or, in other words, negative 1/2 x to the negative 1? Well, the derivative of that would be what? A positive 1/2 x to the negative 2. That's not quite what we're going on. I got the half. Not quite. All right. Try again. Yeah?
X over x.
Yeah, go ahead.
Over 2.
Say what?
X to the negative 1/2. Yeah, radical x over 2. Radical x plus 3.
Radical x over 2. All right, let's try this. Radical x over 2. Okay. It doesn't have to be plus c all the time, okay? Fine. Yeah, Martha. Martha's a constant, I got it. Okay, well, think about it. This is x to the 1/2, right? So when you differentiate x to the 1/2, don't you get the 1/2 already? Right? So do you need the 2 here? No, you don't. That's it, done. X to the 1/2's derivative is 1/2 x to the negative 1/2. X to the negative 1/2 is 1 over rad x. Oh, that's it, done. Okay, that wasn't terrible. Next page. You ready? Just a couple examples to see if you remember how to do any of this stuff. All you need to know is how to differentiate. You don't have to memorize any antiderivative rules, although eventually we probably will. All right, so if I give you f prime, what was f? Realize what we're asking. We're really asking what's the antiderivative of f prime? It's f. Right? That's what we're doing. Okay. All right, so let's try, how about this? 1 over x squared. What do you think? We got that one by accident, didn't we? Do you remember? Someone gave me an f that wasn't right before, but it's right now.
Negative 1 over x.
Negative 1 over x. Let's see. Okay. Plus Martha, right. Yeah, this can be any constant you feel like. Eventually you're going to run out of constants. You don't want to use plus c all the time. If you're, say you have a problem where you're integrating a whole bunch of times. You don't really want to write plus c everywhere because that gets confusing. You might think they're all equal or something. All the c's may not be equal. Oh, is that true? Well, that's really negative x to the negative 1, right? If you differentiate that, the negative 1 goes out in front, so it becomes positive. That's good, right? And then you subtract 1 when you differentiate. X to the negative 2 is that. Oh, yeah, that's good. All right, good. Just checking. It's really easy to check an antiderivative. Differentiate it. Right? So if you know how to differentiate, you're in good stead. Okay, try this one on for size. 10x. Did I hear it? What? 5x squared. Has to be.
Plus c.
Plus gamma.
Oh. C.
Gamma's a constant.
Why didn't we just write c at the time?
Well, you can always write c, but I find that confusing. You always have to have a constant. You always have to have some kind of constant there. I tend not to write plus c all the time. You'll see why later when we get there. How about this? 10x minus x squared? So you already got the 10x part. What's that? 5x squared. But then
X to the third over
minus x to the third over 3, right? Because the derivative of x to the third is 3x squared, and the 3's cancel, right? Plus alpha. Just to be weird. Okay. 10x minus x squared, plus 2. Well, the first part's the same, right? The second term is the same, but plus 2x plus, well, I didn't use c on this page, so we're down. Go ahead, use gamma if you want. All right, so the derivative of the constant is 0, drops out. Derivative of 2x is the 2. Derivative of, whoops, that's supposed to be a 3. X cubed is 3x squared over 3 is x squared. The sign isn't changing, it's still negative and so forth, right? Is this terrible?
Yeah.
You know how to do this, right?
Sí, señor.
Sí, señor. Okay.
Great.
Try it again. All right, so if I give you f prime, what's f? F prime now is rad x.
Two x, 3 halves over 3.
2x to the 3 halves over 3?
Yeah.
Wow, are you sure about that? Plus beta. Well, actually, I like this because differentiate this. What happens to the 3 halves? Comes out in front. 3 halves times 2/3 is 1. That's good. And then what do you do with the exponent when you differentiate? Subtract 1 from 3 halves, you get 1 half. X to the 1 half is rad x, isn't it? Yeah, hey, that's
Yeah, I
good.
was right.
See, he was right. You little face. How dare you? Alrighty. How about 1 over rad x? Two rad x? Is everyone okay with that? Well, check it. This is x to the 1 half.
Wouldn't it be rad x over 2?
Well, let's see. Let's check it. This is x to the 1 half, right? So differentiate x to the 1 half. What happens to the 1 half? Goes out in front. 1 half of 2 is 1. Okay. And x to the 1 half, what do you do with the exponent? Subtract 1 from 1 half, you get neg 1 half. X to neg 1 half is over rad x. Yeah, that's right. That's good. All right. Okay, 6 sine 3x. What do you think? Negative 2 cosine, you said? Of what? Of 3x? No? Okay. Why not? What's wrong with this? The derivative of cosine of u is sine of u du. What's du? 3 times the constant multiple we had already. 2 is the 6. Where did the negative go? Is the negative going away? It should. Is it? The derivative of cosine is negative sine, right? Very carefully.
How do you do that?
Very carefully. How do you do it?
Yeah.
Oh, well, how you do it is U-sub. You remember U-sub? This is actually skipping to the last topic on the sheet I just gave you in 5 weeks from now. So we're skipping a lot of stuff. Isn't that the last topic, U-sub? Okay. Well, U-sub is doing the chain rule backwards. The idea is that someone differentiated something using the chain rule, and they got this, right? Now, there's an inner function and there's an outer function. Remember Mr. Che? He always used to say, find the mother function. Who's the mother function? The mother function is sine. That's the outside function. So who's u? Not the mother function. U is 3x. U is the inner function. So what's du then? That's du dx. I want du. 3dx. Why? Because what I'm trying to do is get something to substitute dx with. Right? I'm substituting 3x with what? With u. And I'm substituting dx with what? d over 3. So it's 2, the integral of sine u du. I replaced dx with du over 3. du over 3. Right? Over 3 divided 6 by 3. Then, now let's do the antiderivative thing. What's derivative is the sine? Negative the cosine. So you get negative 2 cosine u. But u is 3x. That's a u-sub. But that's skipping 4 weeks of stuff. We're not doing u-sub yet. Okay? What we're trying to do is based on what we know about derivatives, we're trying to guess something whose derivative works out okay, right? This is a more systematic way of doing it. Have you ever done U-sub? You've done it, right? Now, I know, what? You did it last year, but did you do it like this? See, I don't do U-sub unless it's a clean substitution. In other words, this step has all x's, no u's. This step has all u's, no x's. Yeah, that's not a good way to do it. Especially since sometimes all the u's and all the x's don't cancel out, and that's a problem. Yeah.
Is there an algebraic way to like do when you have a u and x when you do U-sub?
This is the algebraic way. What do you mean?
Like if you still have x's.
Yeah, if the x's don't all go away, you can't do this by U-substitution. So, well, there might be other methods, right? That's Calc C, integration techniques. We're going to get to that. All right, if U-sub fails, or basic integrals fail that you already know, there are other techniques, and we're going to investigate a whole ton of them. Don't worry. We're going to get to that. We're going to prove the antiderivative 1 over x dx. Yes, we're going to get to that. You didn't like that stuff. Wait, when did you do that stuff? Last year you did ln? Really?
No, not derivatives.
Oh, okay.
We did.
No, Hayon probably threw the ln stuff at you, didn't he?
Yeah.
Yeah, because he's like, well, I need this. Okay. Whether you understand it or not, I don't care. Okay, try this one out for size. Again, I'm giving you f prime, and I want f. The thing whose derivative is just f prime, right? So we're thinking backwards. How about 5 cosine of x over 2? Think about that. Something whose derivative is cosine x over 2. Well, we're not doing U-sub yet. So whose derivative is cosine? Sine. So I need sine of u, don't I? But is that good enough? What's the derivative of just this? This will be cosine u, right? Cosine u du. What's du? 1/2. But I don't want 1/2. No. Wait, my thing went nuts. Come on. Okay. I don't want 1/2 in front. I want 5. So what's the fudge factor? 10. Because if you take the 1/2 times the 10, you get the 5, right? Okay. I know it's a little bit like guesswork. It's not as systematic as U-substitution, but we're not there yet. How about this guy? Similar idea. What goes here? Sine of u, right? But if that's all you have, is that good enough? No, because the derivative of this is what? 2 pi cosine u. Well, I don't want a 2 pi. I want a 1. So what's the fudge factor? Divide by 2 pi, right?
Why?
Because God said so. Why? Because otherwise you'd have a 2 pi in front, that's why. Well, because the derivative of sine of u is cosine u du. What's du? 2 pi would end up in front. Remember, how am I checking this? I'm differentiating this, and I better get that, right? So I better divide by 2 pi to get rid of it. Here I multiply by 10 because I was dividing by 2 and I wanted 5. Here I'm dividing by 2 pi because I was multiplying by 2 pi and I wanted 1. Okay. So just think backwards, that's all. All right, now where do we use stuff like this? Well, we'd use stuff like this to solve differential equations or variable separable initial value problems. Huh? Have you ever heard of variable separable?
Yeah.
Have you ever heard of initial value problems?
Well, it's like where it says like, oh, like f of 0 is 0, so what's...
Okay, here's an example. What if I gave you dy dx is 3x squared? That's a differential equation, an equation with a derivative in it. To solve it, you've got to get rid of the derivative, figure out what y is. Okay? All right, and I give you an initial condition. Y of 1 is negative 1. This is an initial value problem. This is a diffq, differential equation, with an initial value problem. Okay? It's not so bad. Now, the thing is, to get rid of derivatives, I have to anti-differentiate, right? Isn't that the whole point? Anti-differentiation is the opposite of differentiation. But I can't anti-differentiate unless all the y's are with the y's and all the x's are with the x's. Can you separate the variables? dy equals 3x squared dx, right? Now anti-differentiate both sides. As long as dx is in the numerator, it can't be in the denominator, right? And dy is in the numerator, and you got x's with the dx's and y's with the dy's, but there's no y's to worry about. You can anti-differentiate. What is the antiderivative of dy? Just y. What's the antiderivative of 3x squared? We just figured it out before. X cubed plus c. How do you get the plus c? Plug it in. This 1 goes where? In place of x. This negative 1 goes where? In place of y. Okay, so negative 1 equals 1 cubed plus c. This is in the way. And so negative 1 equals 1 plus c, so c is negative 2. So what's y? Y is x cubed minus 2. This is the general solution to your differential equation or initial value problem. This is the particular solution. Why? Because this is a cubic that can have any y-intercept you feel like. But there's only one cubic that goes through this point. It's this one with this y-intercept. So you have to resolve the plus c. You have to resolve the constant. And that's what the initial value is for. Okay? So this gives you an infinite family of curves. Think of it. If you graph this as x cubed plus 0, if you graph this as x cubed plus 1, if you graph this as x cubed minus 3, you get all different functions. They're all just shifts, vertical shifts, right? But there's an infinite number of curves you could choose. This is the only one that matches this derivative and includes this point. This matches this derivative. This matches this derivative and has that point in it. It's almost like a curve fitting problem, right? You're given a point, you got to make sure it's in there. Yeah. Did he say that? Okay. Let's see. Yeah. That's good. All right. So how about this one? Let's say A equals negative G. Okay. Now, A is acceleration. It's a function of time. G is a constant due to gravity, right? G varies with altitude and planetoid. Has to do with what planet you're on and how far from the center of the planet you are, right? So let's say we're on the Earth, and G is, 9.8 meters per second. Okay? So we could say, okay, let's do that. Let's write it down. So what I'm really saying is this. Aren't I? Yes? All right, so can you separate the variables? dv equals negative 9.8 dt. So if you anti-differentiate both sides, you get v is negative 9.8 t plus c. Not always c, but okay. Now, what if I gave you some initial conditions like, v of 5 is negative 49 meters per second. I already said g is negative 9.8 meters per second, right? So, is that an initial value problem? A differential equation with a point? So we can figure out c? Okay, so what do you plug in? This becomes 5, this becomes, so negative 49, that's a 9, equals negative 9.8 times 5 plus c. Alrighty, and so how do you get c? What is it? What? I didn't hear you. What? It is 0, right? Is it? Yeah, it is. Because 100 times this is negative 98. But this is half. Sorry, 10 times this is negative 98. That's half of that. Half of negative 98 is negative 49. So let's add 49 to both sides, and we get c is 0. So now I get that v of t is just negative 9.8 t. Okay. How about this? If v of t is negative 9.8 t, then what's s? Isn't v just the SDT? The SDT. And let's say I give you an initial condition like, I don't know, S of 0 is 100 meters. So now what? Separate. ds equals? Separate. 9.8 t dt. So when you anti-differentiate, you get S equals negative 9.8 t squared over 2 plus a constant. And by the way, half of 9.8 is 4.9, isn't it? So might as well write that. S is negative 4.9 t squared plus a constant. That's a t. Yeah, it's still a t. Okay, and what do you do now? There's the conditions. T is 0 when S is 100. So 100 equals negative 4.9 times 0 squared plus c. But this is, so c is 100. So the particular solution is S equals negative 4.9 t squared plus 100.
Was that first t though?
Which t? This t? Yes, we'll talk about that. Why that's there. We don't know why that's there yet, but we'll talk about that. Hang on. That's important. We'll get to that. All right. Now, let's do this more in general. What if dv dt is negative g? So I don't know if it's 9.8. I don't know what the units are. I don't know what planet I'm on. I don't know what the altitude is. Whatever the hell it is. Right? And I give you a v0 is something. And I give you an s0 is something. Can you find s as a function of t? Okay, let's do it. Separate. dv equals negative g dt. Anti-differentiate, you get v equals negative gt plus, let's say, a. How do you get a? Plug in 0 for t and some constant v0, whatever the hell it is for this, okay? So a is, it's just v0. So you get that v is negative gt plus v0. Okay. Now, if v is negative gt plus v0, that means that d s dt is that. All right, separate. ds equals negative gt plus v0 dt. Anti-differentiate, what do you get? Yep. t squared over 2 plus v0t plus some other constant. That's why I don't use c all the time. Okay. And remember, I gave you s0 was s sub 0. Right? So, s is s sub 0, whatever that is, some constant. And t is 0. So b is s0. So here's your general solution. Here's the particular one. S of t is negative g t squared over 2 plus v0t plus s0, which is the Galilean freefall model without air resistance. Now, if you compare that to the previous solution, look, negative g over 2 is the coefficient of t squared. v0 is the coefficient of t, and s0 is all by itself, right? What does that tell me about this solution? That's negative g over 2, right? That's s0. What was v0? What was v0? There's no t term. How many t's do you see? 0, so that's what V0 is. All right, that's all she wrote. Yep.